Okay, thanks for coming today, and sorry about that. Basically, I've got an interest in quite a lot of areas of physics, cosmology in particular. So this talk is mainly about cosmology. So these are kind of the few main players in the history of cosmology. Galileo, Newton, Friedman, Einstein, and I'll talk about them. So I think the main thing that got me into physics in uni was the fact that there are lots of random things in maths. So calculus, tensors, which you probably won't have heard of, group theory, which turn out to be intimately related to lots and lots of different parts of physics. And you wouldn't necessarily know this, but it's something that got me into physics anyway. So just to give you a bit of background about myself, you might have heard from my accent, I've got a kind of American twang to it. So I grew up in London. My dad's British, he works here, his name is Grant. He used to be a Marine in Northern Ireland. He grew up in London, he was born in Wales. He was an orphan and he started working here 20 or 30 years ago. Yeah, and my brothers are Arthur, Fred, and Edward. Probably some of you know them. Arthur's in the US. Yeah, so that's kind of the two main pictures that come up when you search Sydney, Nebraska on the internet. That's where my mum grew up, on a farm. So that's Crazy Horse. That's the kind of history of this area. Native Americans. There are a lot of Native Americans around that area. Anyway, this is where I grew up. I grew up in a council estate in Westminster. That's the building near Regent's Park, near the London Mosque. And I went to a state school in central London called QK. Kind of got its fair share of problems, gangs and things like that. But it's quite a posh area. So I grew up in quite a posh area of London near Abbey Road. So there's kind of quite a big contrast there. Anyway, finally we get to university. That's Imperial College. Yeah, that's where I spent a lot of my time for the past, I guess, 4 years, because I did an M.Sci. physics degree. I just graduated this year. This is, it's a picture of where I was doing my M.Sci. project. The picture isn't that good, but I was basically using a pressurized gas container here to shoot a metal bar at some polymers to squash it, and that's all you need to know about that. It's not the most interesting project, to be honest. But yeah, so while I was in Imperial, there were lots of things that challenged me, lots of things I found difficult, but I found that I got more into it as time went on. And I think the biggest thing that happened to me is you start off like this, you think you know everything, and you think that there's this small part that you don't know, and what happens over time is something like that. So, you basically realize that you don't know anything about the subject, and that sort of happens time and time again. And you come into contact, yeah, I quite like these memes. So, yeah, you come into contact with really intelligent people, you realize, there's people who are so much smarter than you, and it kind of broadens your horizons quite a lot. But anyway, onto the main topic. Just before I start that, I also started a PGCE physics training course this year. So it basically means you teach in 2 schools. First one was a Church of England school, kind of a bog standard school. Second one is a Jewish school, a really high performing school, and that's where I was today. Just a couple hours ago, I was teaching year 8 electricity. So, yeah, okay. Anyway, to get onto the topic, I think this picture off the internet is quite interesting because it sums up a lot about cosmology. It sums up how far we've come. So, obviously this is probably it didn't come from a scientific journal in the medieval ages, but the point is, it gives you this idea. They used to think that outside of the Earth there was this celestial sphere, kind of the heavens, and that was unchanging, that was eternal, and that was governed by different laws from the things on Earth, and there were 2 separate things, and they thought there were kind of spheres along which the planets were embedded in. I'll get onto that a bit later. But one of the main things which is obviously wrong is one of Aristotle's idea. He thought that 4 elements make up the universe: fire, earth, fire, air, and water, and he tried to use that to explain gravity, for instance. That didn't really work. So also in the Greek ages, we have Ptolemy's solar system. So we've got this really complicated geocentric model. I mean, one thing you probably know about the medieval ages is some people were persecuted for promoting a heliocentric model, and that basically started around this time because it was from about 300 BC until kind of the late 17th century that people believed in the geocentric model. So it's really only recently we've come to realize that we don't orbit around the Earth, or that the planets don't. So anyway, I mean, if you look at it, it's a bit complicated, but to explain the motion of all the planets, all the stars, you have to come up with all these ad hoc fixes. And that ad hoc basically means you believe in a theory, and so you come up with more and more sort of random things to explain observation. So that's kind of like, that's a bad way of doing physics. So essentially on each planet was orbiting around a point, which was orbiting around another point, just going to lots and lots of complicated physics to explain something quite basic if you accept that it all orbits around the sun. Yeah, and this became part of Christian dogma in the medieval ages. So one of Copernicus's friends in, I think, the 15 or the 1600s was burnt at the stake for promoting a geocentric model because people were so wrapped up in this idea that they refused to basically accept what the evidence was telling them. Yeah, so his name was Gordiano Bruno, and he was burnt at the stake in the 1600s. But I think the Copernican model is where we first come to a kind of modern understanding of the solar system, is where we come to the idea that actually the Earth isn't anywhere special. The Earth is just one planet among many in the universe. So then we get to Kepler and Newton in the 1600s. Those are some of Newton's achievements. Obviously, it's quite impressive. But the important thing about Kepler is he discovered that all of the planets orbit in particular elliptical trajectories. They orbit in ellipses. And what Newton realized is with a particular force, a 1/r² gravitational force, you can explain all of that, and you can also explain why apples drop to the Earth. So you can use the same physics to predict what's going on in the solar system as you do to predict what's going on in the Earth. And that's quite a sharp break from what people had thought before in the Middle Ages. So if you know anything about Einstein, you might know even at this point there's already a problem. One of the things with Newton's theory is it says that if you have a mass here and a mass here, then the gravitational force between them is instantaneous. So if I move this mass, then instantly this mass feels a new force. So that's a problem for a reason I'll mention in a minute. But there were other issues, like it didn't explain all of the motion of the planets in the solar system. So some people thought, well, there has to be something more. And this kind of culminated in the beginning of the 1900s with something called the Luminous Ever. And basically what this was is they were trying to figure out what does light travel through, what does visible light travel through. And so they did this experiment in different parts of the Earth. And they said, well, if I'm moving relative to this background medium that the light is traveling through, then surely the speed of light is going to be different to what I would observe if I measure it while moving at this angle. But what they found is the speed of light, it doesn't depend at all on which way you're moving. It's a constant. And this, you probably know where I'm going now, this basically culminated in Einstein's special theory of relativity. So it says the speed of light is the same for all observers. It doesn't depend if you're moving at 100 miles an hour or half the speed of light, you always measure it to be the same thing. And the reason that's important is because it unifies two things that people thought were separate. It unifies space and time. So exactly why it does that? Well, mathematically, that's the only way for all observers to measure the speed of light to be constant in every part of the universe. But kind of more importantly than that, it takes you from this geometry we thought we were living in, called Euclidean geometry, the geometry that the Greeks thought described the world, which is three-dimensional, which is flat, and where you can use Pythagoras' theorem, to a more complicated geometry called Minkowski space. So, I mean, in terms of what it is, we'll simply put it's basically extending this three-dimensional space, which people used to think we lived in, to a four-dimensional space-time. I mean, that probably sounds quite complicated. The maths looks a bit complicated. But basically, this is what you sort of already know as if an object is moving at a particular velocity, then you have these equations that allow you to transform between different coordinate systems moving at different velocities. I mean, I won't go into that, but the point is that, like it says here, time and space can be rotated into each other. I mean, that's a bit of a simplistic way of putting it, but the point is that time and space are no longer separate things. They're linked. So, I mean, to put it one way, if you lived in a two-dimensional space, you didn't know anything about height, about the third dimension, you could rotate this remote control in this two-dimensional space, and you might say, well, the component along the x-axis is changing, and that's fine, because we know it's just rotating into the y-axis, right? The length of the controller is not changing. But if you didn't know anything about this third dimension, you might take this controller, move it up, and you might say, well, that's a bit odd, because the length of the controller within this two-dimensional space seems to be changing. But it's not odd. The controller's length is the same. It's just, well, actually, there's a third dimension. So, I mean, that's kind of a good analogy, I think. This idea that if you move faster, if you change your velocity, then it's a bit like taking an object, for example, the separation between two stars, and rotating that in this abstract space. I mean, basically, that leads to all of the strange effects you get in relativity. That leads to length contraction, time dilation, to time slowing down, to space squashing. That's basically a consequence of the geometry we live in. So I think kind of the next step on the journey in science is after special relativity. In about 1919, I think it was, Einstein came up with something, his principle of equivalence. I mean, it's a bit complicated, but basically it says, if you're standing on the Earth here, then if you drop an apple, it falls down, accelerates. But if you were in a rocket ship, and the rocket ship was accelerating upwards in free space, away from any mass, away from the planet, if you accelerated by the right amount, 9.8 units, then if you dropped an apple, it would be exactly the same. So I guess it's a bit subtle to understand, but the point is that it means acceleration can't be distinguished from gravity. The reason that's important is because it leads to this idea that actually, in some situations, the gravity is zero. So, for example, when you're falling down an elevator shaft, you have the sensation of floating. But if you're standing on a wooden floor, you've got the sensation that something's pushing up at you, and you have the sensation that something's pulling you down, and that's only in this particular situation. The reason that's important is because, yes, it basically removes this idea of gravity as a force and makes it into something slightly different, which I'll come on to. And this is sort of kind of the natural extension of that. If you drop a tennis ball down, it accelerates downwards. And if you ask someone, why is it doing that? Why does it follow that trajectory? Then, I guess, do any of you know, or what would be your suggestion? So if I throw a tennis ball in the air, why does it travel in that particular trajectory, that particular path? Or what would sort of be the intuitive answer, do you think? Yeah, you threw it, but why doesn't the tennis ball do this Why did it travel in like that particular shape?
Because of the force that you put on it when it left your hand.
Yes. So you gave it a momentum, you gave it a kinetic energy, so it's moving in that direction. But what's stopping the tennis ball from moving in a really crazy path? So, I mean, I guess the main things you might say are the equations of motion. The equations of motion of a system tell you how it evolves with time. That's kind of the main answer. I've written here two other things. So Fermat's principle, this is kind of analogous. It tells you that light rays always basically travel in straight lines. So it's the thing that tells you how a light ray will evolve in time. A light ray will evolve. And there's something called Hammond's principle, which I won't get into, but which is also related. So yeah, anyway, what I was getting onto is that these trajectories are special. If you throw a controller, it doesn't travel like this and land over here. It travels in a really specific line. So out of all the kind of random trajectories it could take, it travels on a very specific one. And that's what a geodesic is. So, I mean, you've probably heard of a geodesic before if you've read any popular science books. If you look at the surface of the Earth, then often people explain it as it's the shortest distance between 2 points, and that's true. But it turns out that that's what physical trajectories correspond to. If you throw an object on the planet Earth, it always follows a geodesic. And where I was leading to is this idea that geodesics are the trajectories that objects want to travel along. So, I mean, does anyone remember what, like from A-level physics or something, do you remember what Newton's first law is? Yeah.
Body motions, body velocity stays at constant velocity until force that.
Yeah, so basically it says the velocity is constant. It travels in a straight line unless a force acts on it. So that's basically like the inertia of the object. The more inertia it has, the more it kind of wants to follow a straight line. And the more inertia, the more mass it has, the harder it is to accelerate it. So, yeah, where I was leading to is that if you say we no longer live in a flat space, like the Greeks believed, if you no longer live in a flat space like special relativity describes, a flat four-dimensional space-time, if in fact we live in a curved space-time, a curved four-dimensional space, then the conclusion naturally is that rather than using Newton's first law and saying the tennis ball is going to travel in a straight line when no forces are acting upon it, what you have to say is it's going to travel in a curved line. And that's what leads to all the kind of the interesting effects with gravity. So just out of interest, does anyone know how this is related to gravity? Or how it's related to the presentation? Just wondering. Okay, so basically, I mean, the objects, when they're spinning round, they're accelerating, aren't they? They've got the tension in the wire that's keeping them going in a circle. And when they're going round, they feel these forces. Does someone know what the centrifugal force is? Yeah. Yeah, so it's like something that pushes it out. So if you go on a roundabout in a playground and you start spinning it faster and faster, you have to hold on tight or else you kind of fly off, right? There's the Coriolis force, which is to do with hurricane formation. It's something similar. It's basically because we're rotating, we're orbiting, we feel this force pulling us out. And so we might say, oh, well, there's this physical force, and we might name it the centrifugal force and kind of come to the conclusion that there exists this force in nature called the centrifugal force. But if you know any physics, you know that the centrifugal force isn't a real force at all. All it is just this natural tendency of our body to move in a straight line. And so as we hold on to this roundabout, our body has this natural tendency to move in a straight line. We're resisting that. And so we feel this force. And so we call it a fictitious force. So I'm taking a while to get there, but basically that's what gravity is. Yeah, so the reason I put this picture up there is because if you imagine he's stationary, his kind of jetpack thing is holding him at a constant height, then we might say, well, gravity is balanced by this upward force of the jetpack, so he's in equilibrium. The interesting thing about general relativity is what it says is that gravity doesn't exist, it's a fictitious force. So the only reason he feels this force pulling him downwards is because his body wants to travel along a geodesic, a particular trajectory through space-time. So I mean, I guess that sounds a bit complicated, but the point is that it would be natural for his body to move along this path to fall down. And because he's resisting that with his jetpack, he feels a force of gravity. I mean, I think a useful way to explain it is if you jump off a building, you feel like you're floating. And from this perspective, well, that's because there is no force acting on you. You're just following a geodesic through this geometry. You're just following a natural trajectory. But because he's resisting that, he feels this force. So I guess I won't go over this too much because it's a bit mathematical and obviously that's not good. So, I mean, if you want to look at what determines how the system evolves, what determines how the geometry evolves, you have to look at the equation of motion. So the equation of motion is something like F equals ma. It says if you apply force, then the tennis ball moves in this particular way. Or it's like Faraday's law, which says that the electric and magnetic fields evolve in a particular way. So this is a lot more complicated. It's 10 differential equations, 10 equations. They're nonlinear. And if you've heard something about chaos theory, then nonlinear systems are generally associated with chaos theory, things that are very hard to predict, like the weather system, basically difficult to solve. So it's difficult to find solutions. I mean, you can find some solutions to these. One of them is called the Schwarzschild solution, and that's basically spherically symmetric. So for example, if you look at a black hole, you've got lots of energy concentrated here, and you've got this spherical symmetry. And so the geometry also has this spherical symmetry. So you can find these exact solutions, but it's quite difficult. Then there's also something called perturbation theory, which is basically approximating these equations. It's taking a really simplified form. And if you do that, and you assume objects are moving really slowly, slow compared to the speed of light, and if you assume the gravitational field is really weak, then what you find is you just recover Newtonian physics, Newtonian gravity. And that's important because it's an example of what we call the correspondence principle in physics, which basically means that all of our theories, all of our most complicated theories, they can always be approximated as something very simple. So something like quantum mechanics, you can often find situations where you can recover classical mechanics from it. So for example, if you have a chair, the equations of motion for each atom are really complicated. But on the aggregate level, when you've got lots and lots and lots of molecules, you find it obeys classical physics. So let me just go here. So there's kind of a few effects of this. Einstein showed that you get this gravitational lensing, gravitational bending of light. That was discovered by Arthur Eddington. Who's this guy? People didn't really believe him because he was a fan of Einstein. They thought that maybe he had kind of subconsciously wanted to get that data. And that's part of the reason Einstein didn't get a Nobel Prize for general relativity before he died. So there's also this effect, which is basically planets don't orbit in this trajectory like this. What happens is this whole ellipse shifts. It rotates over time. And the value predicted by Newton is about 1.5 degrees per century. So this is really exaggerated. The value predicted by Einstein is very slightly more than that, like 43, or a few thousandths per century, but you can measure it. So finally, the kind of third main piece of evidence for general relativity is this thing you might have heard about in the news. So this is an example of a binary star system, like two neutron stars. This is a simulation I got off Google. So basically, obviously it's kind of a simplification, but it's supposed to show you this rippling oscillation that's emitted from the system, kind of similar to how a charged electron can emit electromagnetic radiation. And there's this facility in the US that's quite big. It's like 30 kilometers wide. And basically what it is you've got these 3 points in the US, these 3 laboratories that are connected by arms with light traveling down the paths. And you can use that to observe these effects, to observe gravitational waves. I won't go into that. Yeah, so finally we get to, I guess, still the early 1900s. Hubble observed that galaxies are moving away from us. Friedman worked out how that evolves in time. And then we get to sort of modern cosmology. We've accepted the Big Bang. We've accepted Hubble's law. The universe is expanding. And we get to a few quite interesting problems in cosmology. So for example, the flatness problem. We could have a flat universe, which it turns out it is roughly. We could have a curved universe, lots of different types of curved universes, kind of, those are the two main examples. But our universe happens to be really, really flat. And the problem with that is, why is that? That's the problem. The problem is there's nothing forcing it to be flat. And it just so happens we've kind of miraculously found ourselves in a very, very flat universe, and physicists like to have a reason for everything. Another odd thing is, I don't know if you guys recognize this, it's the cosmic microwave background radiation. So it's basically light from all around us, and we find that it's all at this temperature of 2.7 degrees above absolute zero, with really, really small fluctuations of like 1/100 of 1%. The problem with that is, most of this light here, and this light here, and this light here, and here, and here, has never been in contact. These parts of the universe all evolved separately, and they just happen to all reach the same temperature. And that's called the horizon problem. So there's a couple of these problems that, I gave the answer away. There's a couple of these problems which you basically problems. So it's as if someone had started a clock watch and set it exactly in such a way that we would find ourselves in these really special conditions. I'm not trying to advocate the existence of God, but what I was going on to is inflation. So this is good for physics because it allows physicists to basically find a way to resolve this problem, to find a mechanism that puts the universe in this place. It's a bit complicated, I won't go into it too much. But basically, it's a particular set of particles in the early universe that blew it up by a factor of about 10 to the power of 78 in a really, really short time, something like this time here. And what it did is it spread everything out. It spread the energy out, spread the mass out, made everything very homogeneous, isotropic. It looks the same in every direction, and that essentially solves these fine-tuning problems. It solves all of that. So we're getting quite close to kind of the 1980s, 1990s, until we get to something related to this. Does anyone know what that corresponds to in cosmology? Yeah, good. So this kind of first appeared when Einstein came up with his theory. He thought the universe was static, and he thought it was in this sort of equilibrium. And he used a mathematical term called the cosmological constant, represented by that, to arrange it like that, so you get that solution. Problem with that is if a star moved by a small amount, it would all collapse in on itself. It's not a stable solution. And so that was basically disregarded. until it appears again in the 1990s, where scientists realize, well, actually, the universe isn't decelerating in its expansion as it should do because of the gravitational attraction. In fact, what it's doing is it's accelerating, it's speeding up. And so we get to this idea that there's this strange substance called dark energy, which contributes about 72% of the energy of the universe. I've skipped over dark matter, which also contributes a sizable amount. And we're left with only about 5% of the universe being kind of what we know as ordinary matter. So we can describe this bit of the universe, and all of this basically we don't know a whole lot about, especially dark energy, because that's quite weird. So the reason that dark energy gives this accelerating expansion, I guess the math is a bit in depth, but basically, ordinarily energy gets spread out. If you double the size of the universe, you think, well, the energy is more spread out. There's fewer atoms per unit meter. But dark energy is a bit special because the density of it is constant. So if you double the universe, you increase its size, it doesn't dilute. There's suddenly more of it. So it's as if space itself has this energy associated with it. And that's called vacuum energy. So there's kind of a few different ideas about what causes vacuum energy. I guess I won't say too much about that because I think it's quite complicated. But those are sort of some of the problems facing cosmologists in the 21st century. What's dark energy? What is the vacuum energy? And I realized I didn't explain what this biggest discrepancy is. Basically what it is the theory. We've got an estimate for how much dark energy there is, and we've got the observation of it, and those two turn out to be different by a factor of 10 to the 100 or something like that, which is the biggest discrepancy in the history of science. So that's one of the problems facing us today. So this is getting kind of close to the end. Basically, what do modern cosmologists do? Well, they try and predict how the universe evolves. They find models to predict it. They try to rule out models. That's generally theoretical physics, theoretical cosmology. And then physical cosmologists, they sort of, rather than looking at the really complicated theory like quantum theory, string theory, they try to model the bits of the universe we already know about. So, yeah, okay, so what's the nature of gravity? Well, we know that we've got these three forces that are really important: the electromagnetic force, the weak force, and the strong force. And those are all quantum theories that describe them. We know this theory of gravity we have is not a quantum theory, it's a classical theory. So you don't have anything like Heisenberg's uncertainty principle in it or anything like that. And we know that generally in physics what happens is that separate phenomena in physics get unified into one theory, and you find out that they're really part of one underlying phenomena. So that's what happened with electricity and magnetism. That's what happened with electromagnetism. That's what happened with electromagnetism and the weak force. That got unified into the electroweak force. So I don't know if you've seen the Stephen Hawking movie Theory of Everything, but that's what the theory of everything is referring to. So it's referring to this unification of all the forces, which I suppose you could say is the ultimate aim of a lot of theoretical physicists. Because all of the theories we have right now are what you call effective theories. They're only valid within a particular range of conditions. So you could say that's kind of the whole effort of physics. It's finding this one ultimate theory, or I guess that's how some people would put it. So yeah, I think we've come a long way since kind of Aristotle's idea of these four elements. But basically the main idea of science is the same as the thing you come into contact with at university or at school. And it's basically asking deep questions about why things happen. I think that's the end of my talk, so thanks for listening.